As per the question, the fast ionization constant of H2S is given, that is K1. We have to calculate the concentration of HS minus in its 0.1 m solution. This is the first part. The second part is how will this concentration be affected if the solution is 0.1 m in HCl. So this is the second part. And the next part is the second dissociation constant of H2S is given, that is K2. We have to calculate the concentration of H2 minus under both the conditions. So we have four parts in this question. So in the first part, let us find out the concentration of HS minus in its 0.1 m solution. So if H2S is dissolved in water, it will produce HS minus and H3O plus. This is the K1, which is given as 9.1 into 10 to the power minus 8. So if initially the concentration of H2S is 0.1, so concentration of HS and H plus ion will be 0. Let X amount of H2S is dissociated in water. So the concentration of H2S at equilibrium is equal to 0.1 minus X. The concentration of HS and H3O plus will be X. So if we write the expression for K1 and putting the value, we will get 9.1 into 10 to the minus 8 is equal to X square divided by 0.1 minus X. We can see the value of K is in order of 10 to the minus 8. That means it is very less than 10 to the minus 3. So the reaction is just started. So we can say the dissociation is very less. So the value of X is very small than 0.1. So 0.1 minus X is equal to nearly 0.1. So substituting the value, we can find the X square is equal to 9.1 into 10 to the minus 9. Now we have to find the square root. The square root of 9.1 into 10 to the minus 9, which can be written as 91 into 10 to the minus 10. So we know the square of 9 is 81 and the square of 10 is 100. So we can say this 91 is in between 81 and 100, approximately in the middle. So let's try for 9.5 square. If we multiply 9.5 with 9.5, it will become as 90.25, which is nearly equals to 91. So we can say the value of X is nearly equals to 9.5, and the square root of 10 to the minus 10 will be 10 to the minus 5. So this is the also concentration of HS minus. So we can say the concentration of HS minus is equal to X, which is equal to 9.5 into 10 to the minus 5, which is also the concentration of H3O plus in this K1 expression. Okay, in the part 2, it is given we have already 0.1 m HCl. See, we have already 0.1 m HCl. So initially we have 0.1 m HCl and 0.1 m H2S. So at equilibrium, let X amount of H2S is dissociated. So this will be 0.1 minus X. HS will be X, and the concentration of H plus ion will be 0.1 plus X. So this is the concentration of H plus ion. Again, if we write the expression, the K value does not change with change in concentration. It will change only with the change in temperature. So it will remain constant. Again, by putting the values of the concentrations, we will get 9.1 into 10 to the minus 8 is equal to X into 0.1 plus X divided by 0.1 minus X. But as the K value is in the order of 10 to the minus 8, so dissociation will be very less. So X must be very less than 0.1. So we can say 0.1 plus X is equal to 0.1 minus X, which is equal to 0.1. So by substituting the value, we'll get X is equal to 9.1 into 10 to the minus 8, which is the concentration of HS minus. So in second case, the concentration of HS minus will be 9.1 into 10 to the minus 8. By comparing these two values, we can say when we add the acid, the value of concentration of HS minus decreases. So again, coming to the third part, it is asking for the H2 minus concentration if the second dissociation constant is 1.2 into 10 to the minus 13. So from the first part, the concentration of HS minus is 9.5. See, 9.5 into 10 to the minus 5. Also, the concentration of H plus ion, which is equal to S, is equal to 9.5 into 10 to the minus 5. So when we write down the equation, the concentration of Hs minus is 9.5 into 10 minus 5. Also, the concentration of H plus ion is 9.5 into 10 minus 5. Now at equilibrium, let X amount of Hs is dissociated. So this will be minus X and this will be X plus 9.5 into 10 minus 5. So if you write the expression for Ka2, this is the expression. Again, by substituting the values, we know this is the Ka2 is in the order of 10 to the minus 13, which is again very less. So X must be very less than 9.5 into 10 to the minus 5. So 9.5 into 10 to the minus 5 minus X must be nearly equal to 9.5 into 10 to the minus 5. Similarly, the 9.5 into 10 to the power minus 5 plus X will also equal to 9.5 into 10 to the power minus 5. So again, by substituting the values, this will be cancelled out. So we will get X is equal to 1.2 into 10 to the minus 13, which is the concentration of H2 minus. In the second part, we all know in the second part the concentration of Hs minus is 9.1 into 10 to the minus 8, and the concentration of H plus is nearly equal to again 0.1, because the value of X is very small. So by substituting the values, initially this is 9.1 into 10 to the minus 8 and the concentration of H plus ion is 0.1. If X amount of Hs is dissociated, this is the concentration of Hs minus, and the concentration of H plus ion will be 0.1 plus X. Again, the value of X is very small than the 9.1 into minus 8, which is again very small than the 0.1, because the dissociation constant is in the order of 10 to the minus 13. So the dissociation will be very less. Again, by substituting the values, this will be equals to 0.1 and this will be equals to 9.1 into 10 to the power minus 8. So when we calculate the value of X becomes 1.2 into 10 to the minus 13 into 9.1 into 10 to the minus 8 into 10. By solving this, we will get this will 1.092 into 10 to the minus 19, and this is the concentration of H2 minus, which is equal to X. So this is a little bit lengthy, but we have to solve this. If you solve this once, it will become very easy, but we have to do the calculation in a wiser way, so that we can complete it timely and get a very approximate and right answer. So join with us. Happy learning.